All right, quiet now. We're going to talk about ions and compounds, and when we're done, you should be able to do the stuff that's on the back page of what you were just working on. And so before we really get into ions and compounds, we want to talk about a special kind of electron called valence electrons. Valence electrons are the electrons in the last shell or the outermost energy level for that atom. If you recall from our previous notes, the number of electrons that can be in any one shell is limited. The first shell, which is basically just hydrogen and helium, can have only 2 electrons. Okay, the second shell could have 8. The third shell could have 8, and then we go to 18 and 18, and finally 32 and 32 for the last 2 shells. The thing is, if an atom has more than a certain number, like say sodium, which we've been looking at, sodium has 11, well, the first 2 will go in that first shell, the next 8 will go in the second shell, but that only gets us to 10. The 11th one will be in the third shell. And so the valence electron is talking about that last electron that's in that third shell. And basically there is a pattern that works out for the periodic table in which everybody in column 1 has 1 valence electron. So they all have 1 electron in the last shell. They just have a different number of shells. So for example, hydrogen, 1 shell, 1 electron. There's only 1 in the last shell. It's only got 1. But then we drop right down to lithium, 2 shells, but only 1 electron in that second shell. And then sodium, 3 shells, but again, only 1 electron in that third shell. So everybody in column 1, which you were coloring just a moment ago as the alkali metals, everybody in that group has only 1 electron in their last shell. Then you move over. The alkaline earth metals have 2 electrons in the last shell. We then skip the transition metals because they do not fit the pattern. And we get to boron. Everybody in that column has 3 in the last shell. Carbon, 4. The nitrogen phosphorus column has 5. Oxygen's column, 6. The halogens, that's another group that you were coloring up. Next to the last column, they have 7. And then the last column has 8, with one exception, of course, is helium. Helium being in the first row can only have 2 electrons. So those are valence electrons. Now, why do we care about valence electrons? Because basically every atom would like to have nothing but full shells. Okay, well, the noble gases, those ones that all had 8, they have nothing but full shells. Every single one, helium and then neon and argon and krypton, they all have completely full shells. None of them are partially filled. Everybody else on the periodic table has partially filled shells. Well, all those other atoms want to be like the noble gases. They want to have their shells full, or the outer shells could be empty. Like hydrogen has only 1 shell to fill up, all the other ones would remain empty. Atoms can either gain or lose electrons to fill up those shells or to empty them out. Okay, but the only electrons we're talking about are the valence electrons, the ones that are in that last shell. And for example, fluorine, which we've looked at already, fluorine, which is number 9. Now if you think about it, it's number 9. It has 9 electrons, but those 9 are divided into 2 shells. The first shell, it's got 2. The second shell has 7. But if it had 1 more, it would be like neon. Right next door to it, number 10, it would have 2 full shells. All the rest would be empty. So if it can gain 1 more, then it would be just like neon. It would be like a noble gas, and it would feel complete. Now, in gaining that 1 extra electron, it would become an ion. The noble gases, by the way, and we'll see this more in a moment, but the noble gases, of course, are already full, so they don't become ions. They're not going to lose or gain any electrons because their shells are already full. Everybody else, however, has partially filled in that outermost shell, that outermost ring, and so that's what they're going to fill up with. Now, as I said, ions are atoms that have lost or gained electrons. We write them with what are called superscripts, kind of like an exponent. But the exponent has a positive or negative sign. So, for example, for aluminum, you see the 3+ there. That designation tells you it's an ion, that it's not just an atom, that in fact it has lost or gained electrons. If it's a positive ion, it has lost electrons. And so aluminum, which is number 13, remember the atomic number tells us the number of electrons. It's number 13. It also tells us it's the number of protons, which are equal. So you see 13 electrons, 13 protons. They cancel each other out charge-wise. Atoms are neutral. But as an ion, the aluminum lost those 3 electrons in its last shell, those 3 valence electrons. And by losing them, they no longer have the same number of electrons and protons, and so now have a charge. Because there are more protons than electrons, it ends up being a positive charge. And since it's 3 electrons they lost, it's a positive 3 charge. Now, as you might guess, if the ones that lose electrons become positively charged, the ones that gain electrons will become negatively charged. And so now we have the negative ions. And oxygen is a perfect example. Oxygen has 8 electrons, it's number 8, has 8 protons. Again, normal atom, they would cancel out, no charge, atoms are neutral. But as an ion, the oxygen atom gained 2 electrons to get to 10, again to kind of be like neon, the closest noble gas on the periodic table to oxygen. And because it has those 2 extra electrons, it's now going to have a negative 2 charge. Now, I might point out these notes are related to the exact kind of questions that you would get on a quiz or a test. In other words, you will be asked, hey, what kind of charge would this have as an ion? for aluminum or oxygen, or basically any of them in certain areas of the periodic table. The one place you might guess we wouldn't is where we have that skip spot, because again, they don't follow any particular pattern or rules. But that would be a kind of question, hey, what kind of ion does oxygen make? Well, it makes a -2 ion. What kind of ion would sodium make? And it turns out it'll make a +1 ion. So those are the kind of things that you're going to have to be familiar with, as well as the pattern, because there is a very noticeable pattern for how the ion charges go across the table. Justin?
I have a question. Are we given the whole,
Oh, you'll get a periodic table all the time, but you won't have the patterns actually listed for you. You'll have to just know what the pattern does as you go across the periodic table. And I'll show that to you in just a moment. But yeah, you'll always have a periodic table pretty much for the rest of the year on any quiz or test that you do. It's mostly a matter of, can you read it? Can you know what the trends are in looking at a periodic table, the way things work, as opposed to actually memorizing any particular value. So the idea will not be to memorize what aluminum is or what oxygen is. It's to know what the trend for charges are. And so then you just kind of walk your way across. You go, oh, it's in this column, therefore it's going to have this kind of charge. That'll be the idea. So you might say, all right, some of them are positive, some of them are negative. How do we tell? What's the deal? Well, really, it comes down to atoms take the easier path. Nature likes to take minimum values in things. Don't use any more energy than you have to. And it's true for atoms to become ions. So, one of the things is aluminum can lose those 3 because the alternative would be to fill up the shell. And it'd have to get 5 more electrons to fill up the shell. So it's a little bit easier just to lose 3 than it is to gain 5. Likewise, for oxygen, it's already up to 6. It only needs to gain 2 more electrons to fill out that second shell. That's easier than losing all 6, because whether it's losing or gaining, it's going to require a certain amount of energy, and basically that energy is what happens in the chemical reaction. There's going to be a certain amount of energy to either lose or gain electrons. And so it's going to take the easier path to get there. Aluminum will lose those 3. Oxygen will gain those 2. And basically, if you look at the table, you can see that ones on one side tend to lose, ones on the other side tend to gain. And really, it's kind of in the middle that it's a little bit more up for grabs, because, when you're halfway, well, you could go either way. Now, really important point, because just as you had some questions on the last test about, hey, how many protons or neutrons or electrons, you're going to get asked similar questions this time too, but now you also have to consider ions and compounds for those kind of questions. And that's what the backside of that sheet will be working on. And here's the thing. Protons, neutrons, the mass do not change just because it becomes an ion. The only thing that's going to change the number of electrons. And honestly, since we don't count the electrons in terms of mass, because remember they're 1,800 times smaller, losing a few or gaining a few is not going to change stuff much. And so we don't worry about them. That's 3-4 decimal places. We're not going to worry about it. So in general, if I look at an aluminum atom, I see 13 electrons, 13 protons, 14 neutrons. Remember, the neutrons come from the atomic mass rounded, subtract the atomic number, so 27, the big number, subtract 13, that gives us 14 neutrons. The aluminum ion, same mass, same number of neutrons, same number of protons, electron number is different. Kevin. So that's all that's going to change is the number of electrons. very easy mistake if you're not paying attention when you read a question. Did it have the word atom? Did it have the word ion? Okay? Now if you're doing protons, it doesn't matter. It's going to be the same number for whichever element you're looking at. But if you're looking at the electrons, it will be a different number for the ion versus the atom. Now, as I said, there's a trend. And that's really what you're expected to know is the trend. And then from the trend, you say what any particular element has. So what you can see is over here, everybody in column 1 is going to be a +1 charge. They all had 1 electron in that last shell, so they're all going to lose that 1 electron and have a +1 charge. Everybody in column 2 is going to be a +2 charge. We skip the transition metals. That's that big block that you colored all the same. That's the one that has all of our expensive metals like gold and silver and all of the metals that we use like for electronics, copper, wiring, and so forth. So we skip that area because they don't follow the pattern. And then once we get over to boron and aluminum, they all become +3. Carbon, it's hard to read there, but that says ±4. Now honestly, instead of writing this down on your notes, what I recommend is you take out the periodic table that you colored and you put that trend across the top and you label it ion charges trend. Okay, so that every time you look at the groups there, you're also being reminded of the charges. Okay, so +1 for column 1, +2, skip, +3, ±4, and then -3, -2, -1. Notice 0 for the noble gases. They're already full. They don't make ions. They do not combine with other elements. We call them inert, which actually is spelled I-N-E-R-T, even though I always pronounce it inert. Which means it doesn't react. And it doesn't react with other elements, not like sodium did yesterday in the demonstration. It doesn't react because it's already full. And everybody else reacts to make shells full or to empty out that last shell. Now, if we put both trends together, you can kind of see how the pattern goes. When I have 1 valence electron, I had that +1 charge. 2 valence electrons +2 charge. Over on this side, because I'm almost full, I'm almost to that 8. When I have 7, I just need 1 more, so that 1 more gives me the -1 charge. And when I have 6, the -2 charge there. And like I said, those are the kind of questions that you would be asked. Not what's the whole trend, but you would be asked like, hey, you know, what kind of charge would sulfur have? You're not supposed to memorize the charge for sulfur. What you're supposed to do is go, hey, here's my pattern, you know, +1, +2, skip, +3. Oh wait, sulfur is in the -2 column. Sulfur has a -2 charge, just the way oxygen does. So that's the kind of thing that you're going to need to know. And again, I would put this on your periodic tables that you colored up. I would put these 2 trends on there. The only one that's a little bit flaky, if you will, it's, you know, carbon's column, silicon, and that because it's halfway. It could go either way, add 4, lose 4. There is a reason we are carbon-based life forms. There is a reason that all of our foods and all of our energies are carbon-based. And it has to do with the fact that it's right in the middle, and it's up at the top, and it basically bonds to more things than anything else does. Now, why do we care about the ions? We care about the ions because that's what leads us to compounds. Because in becoming a compound, those last shells get filled up. For example, if you think about H2O, you know, and maybe you say to yourself, why is it H2O? Why is it not HO or H3O or H2O2? Why is it H2O? Well, if you go back for a second and you think, hey, you know, what was the pattern for oxygen? Well, oxygen is right there. It has 6. It needs 2 more to get to 8. Well, where do those 2 come from? They come from the 2 hydrogens. Each of those hydrogens basically says to the oxygen, hey, here's somebody to share, and 6 plus sharing 2 more, oxygen thinks its entire second shell is now full. At the same time, those hydrogens are sharing 1 electron from the oxygen, so they think their 1 shell is full. Everybody thinks they have a full shell. They have formed a compound to fill up the shells. Same thing with salt. Okay? Sodium, column 1, plus 1 charge. Wants to get rid of that 1 electron. Chlorine, a halogen, right next to the noble gases, only needs 1 more electron to fill up its shell. So the sodium gives away or loses its 1 electron. The chlorine says thank you very much and gains that 1 electron. Both of them now have nothing but full or empty shells. No partially filled ones anymore. It's kind of like trying to drive your car if you drive and you're trying to do it on 3 wheels instead of the 4. Okay? Not to mention you wouldn't want 5 either. You want the number that would fill all the slots. Well, the same thing's going on here. Is they only want the right number to fill the slots. And as we mentioned in the last unit, okay, table salt, entirely new properties once they trade those electrons. Okay? You can eat table salt. It's good for you. Your body needs a certain amount. Not too much, but it needs a certain amount. Sodium, the stuff we saw catch on fire yesterday when we put it into water, would not be a good thing to eat. Okay? Chlorine gas is actually a poisonous gas. In concentrated form, it would kill you. So separately, they're both bad elements, but together they make something that actually our bodies need. Brand new properties when they came together. But why did they come together? So that both of them would have only full or empty shells. Why did the hydrogens and oxygen come together? So everybody would be like a noble gas and have their shells full. Now, there are 7 special compounds, if you will. They're called the diatomics. There's only 7 of them that go like this. So if you were looking at a chemical formula, a reaction taking place, these 7 always show up as 2s. Okay? They always show up as 2s. Everybody else, when you see it by itself, will be a 1. There'll be only one thing there. So when you see iron by itself, it's just Fe. There's no little subscript by it. Only these, which don't have 2 different elements, show up with subscripts of 2s. The number 2 tells you that there are 2 of them. And by the way, if you wanted to know, well, how many electrons, protons, neutrons are the mass of something like this, all you got to do is look at the periodic table, its box, and then double. So hydrogen, 2 protons, 2 electrons, mass of 2. And oh, by the way, still has no neutrons. Okay, because hydrogen doesn't have any neutrons. It's the only one that doesn't have any neutrons. Normally, for the regular number 1 isotope of hydrogen, no neutrons. Everybody else has neutrons. Or fluorine. Fluorine is number 9. So 9 electrons, 9 protons, 10 neutrons because we have 19 minus 9. Mass of basically 19. But F2, 18 electrons, 18 protons. Notice how they match. compounds are also neutral by and large. 20 neutrons and a mass of almost 38. So this is what you should see when you look at compounds. So some of the ones on the back side, okay, some of them would just be individual elements. You just look at the periodic table. Some of them will be these diatomics, and all you have to do is double it. Okay. Also, another thing that sometimes students lose track of, these numbers are down. They're not up. When they're up and there's a plus or minus sign, that means this is an ion. This is its charge. I'm telling you how many electrons I gained or lost. When the number is down, it has nothing to do with charge at all. It just tells you how many of that kind of atom are in the compound. These twos say there's two of them. Okay? If there's no number down there, then we assume it's just one of them. Now, if they're different elements, instead of those diatomics were two of one kind, but here's one, okay? This is a binary compound, binary meaning two things. Sodium chloride. How do I do electrons, protons, and neutrons and mass for compounds? I just add up the pieces. So, sodium has 11 electrons, chlorine has 17, so how many does the molecule, if you will, of sodium chloride? 11 plus 17, it has 28. That's how you do electrons, protons. Mass, same way. Okay, 22.99, 35.453, add them together, you get basically a little over 58. Now, in terms of mass, let me remind you, these masses, they come off the periodic table. They are not for one atom. They are for 1 mole of atoms. Atoms are really tiny. So you need 6.02 times 10 to the 23rd, that mole number. Well, guess what? It's not any different for a compound. Compounds are really little too. I need 6.02 times 10 to the 23rd compounds of NaCl before it actually gets to that 58.443 grams. Remember, one piece of paper, the paper you're writing on is about 5 grams. Okay, so this is not quite 12 pieces of paper, but it takes billions and billions and billions of atoms to get to that point. So it's not for one compound, not for one molecule, it's for a whole bunch of them. 1 mole, 6.02 times 10 to the 23rd. But just add up the pieces and you've got it. And that's why I say, really most of what we're going to be doing in here is just following the trends of looking at a periodic table and how can we use those numbers. There's not very many. How can we use those numbers to tell us all sorts of things on the table? Now, when I do have lots of things, not just one of each, for example, H3PO4 or H2O, those numbers, those subscripts, tell me how many of that particular atom I have in the compound. So here, this means 2 hydrogens and 1 oxygen. When there is no number, it's a 1. We don't write the 1s. Likewise, H3PO4 tells me there are 3 hydrogen atoms, 1 phosphorus atom, no number, so it's 1, and 4 oxygen atoms in each one of those molecules. So H2O, that's 3 different atoms to make up that molecule. H3PO4, that's 8 atoms to make up that one molecule. And so when we talk about how many electrons or protons, whatever, like we just did before, you have to add up all 8 different atoms to know their total. Now it's really not that bad because, of course, if I know what 1 oxygen is, I'm just going to go times 4. So every oxygen has 8 electrons times 4, 32. Has 8 protons times 4, 32. Has a mass of basically 16. We could round it. 4 times 16 is 64. So that's what the numbers down at the bottom tell us, how many of each one there is. And so, again, if you wanted to know how much the whole thing added up to, and this is what you're going to be doing. So if you take that one paper that you colored and you flip it over and you look at the bottom, okay, look at the very bottom there. When it's basically asking you how many electrons, how many protons, how many neutrons, and what's the mass of the compound. This is what you're going to have to do right here, okay, for each one of those. And so, like H3PO4, okay, if I want my electrons, well, there's 3 in each hydrogen, or excuse me, 1 in each hydrogen times 3. There's 15 in phosphorus, and then there's 8 in each oxygen, but I have 4 of them, so 4 times 8 gives me 32. So altogether, I ended up with 50 electrons for H3PO4. Note, I got 50 protons too. They should always match. Protons and electrons should always match for compounds. Now, my neutrons did not match because, of course, hydrogen doesn't have any neutrons. That's the first thing. And the second thing is, for phosphorus, it actually has 1 more neutron than proton anyway. The neutron numbers do change. So you won't always get the same number of neutrons as you do the other two, but those two should match. And then mass, again, hydrogen is 1, 3 of them. Phosphorus, 31, that's its mass. And then 4 times 16 for the 98 for the oxygen part. So you got to add up all those things to get to the totals. Any question on that? I see some faces that might not be sure. Again, this is the homework you'll be working on. You'll start off with individual atoms, then you'll look at a few ions, then you'll do the diatomics, and then you'll get to bigger and bigger compounds. But this is basically what you'll be doing right down there. Oops, jumped too far ahead. This is what you'll be doing right there. All right, we're almost done. Now, periodic table. Okay, it's called a periodic table because things are done periodically. In other words, basically, the periodic table wraps back around so that each row, which is called a period, has similar properties in the same column. So everybody here, remember in column 1, all those guys there had 1 valence electron. They all have a +1 charge. They all have similar properties. So basically, it wraps around to make sure that everybody in column 1 was set up that way. This way, horizontal, across. Okay, those are the periods. Please note, the row number is the period number. How many shells have electrons in them? So sodium, which is right there, it's the first one in the 3rd row, which means it's a period 3 element, and it has electrons in 3 shells. So notice 3rd row, 3rd period, 3 shells. Okay, so it's really important to be able to know what period something's in. And by the way, that would be another question on a test. Hey, what period? Which one of these is the 4th period element? Oh, count down. 1, 2, 3. Ah, it's got to be in that row. Okay, which one of these has 4 shells? Oh, 4 shells, 4th row. Kind of goes nicely that way together. Now, the other way you can look at it is up and down. The vertical columns, this is where they have things like the same number of valence electrons and similar properties. So really, you could say they have been grouped based on, hey, everybody in column 1 has similar properties. The halogens have similar properties. You find them all in cleaning products. Okay, fluoride toothpaste, chlorine in your pool, or chlorine is a cleaning product, clean the floors or something with chlorine. Iodine is sometimes used, in surgery to disinfect. They're all cleaning products. Noble gases are all similar. They're all full shells. They don't bond to other elements. So up and down, things tend to have the same type of properties. And basically, last slide here, the table is ranged, you could say by electrons or by protons, because remember, it's the same number. Elements are ranged so each row repeats, is periodic for the same kind of properties for elements in the same group or column. Okay, but if you think about it, you get in row 3, you got 11, and then next door it's 12, and then you jump across the gap, 13, 14. What's changing there? The number of electrons and protons. You are basically filling up the shell in that row. And then you jump down, you get to the end, argon has 18, 19 is all the way back across. Why? Because number 19 has only one electron in its fourth shell. So that's how it's similar to the ones in the same group.